for the prior knowledge that it should have like a musical background, I guess, musical knowledge behind it. So I found that very interesting. And it's a fielded system. So like right now there are a few customers across the globe, across the world using this, individual customers as well as like businesses. And yeah.
All right, someone else. Oh, good. Oh. Here, excuse me, could you pass this down?
Thanks. All right, so I looked into DeepFace, which is a employed by Facebook, and it's essentially the algorithm they use to scan the faces of people in the image and be able to suggest which of your friends should be tagged in the image. And the fascinating thing about it is that it's actually now working, and it's a production algorithm, and it has scored 97% accuracy, which is pretty high relative to the next generation identification system that's been developed by FBI, which has an 85% accuracy rate. So yeah.
Just predicting cat, I think, is supposed to be pretty good in Facebook.
What's that?
Predicting a cat. Nearly everything is a cat, apparently. Nearly all the videos are cats. Sorry. All right, who else wants to tell us about something? No one else found out anything interesting? Yeah, someone up the back there. Can you just pass it? Does that work? Can you pass it? Oh, here. We'll pass it back. You can pass the microphone back.
So I chose the AI application Google Assistant. It is used inside of the Google Home as well as in the Pixel phones and Pixel books. Something I found very interesting was that DeepMind actually launched WaveNet into Google Assistant. What it is a convolutional neural network that actually allows the Google Assistant to have a more lifelike human voice. So actually Google Assistant, it has a very conversational voice now compared to the iteration just a few years ago. And there's also a couple examples of how it sounds on the website, and you can really see how human-like it sounds compared to the robot-like voice just a couple years ago.
All right. Anyone else? Anyone else? All right, someone over there. Oh, okay. Can you just pass the microphone? No. Yeah, good. Oh. Thanks. Oh, where was it? Here.
Yeah, so there's this game called Dance Dance Revolution, which is an arcade game. And then researchers at UCSD created this algorithm called Dance Dance Convolution, which is the algorithm that generates the dance steps for the Dance Dance Revolution games. It was a breakthrough at a time because no AI system could auto-generate these steps for any music given to the game. They trained it with over like 100,000 different songs in the past. And according to the really enthusiastic Dance Dance Revolution users, the output from the AI system was really accurate compared to the previously human-made dance steps. And the emphasis on the paper was that the network could recognize different sound in any song and also knew which sound to emphasize and then to allocate which dance step to move in a sense that made sense to humans. I found that fascinating and hope to use it one day.
All right. Anyone else? No. All right. All right. Thank you, everyone who gave a presentation. Now, if you gave a presentation, there were bonus marks for giving it. So write presentation on your sheet of paper for doing that. So, all right. All right. All right, so next thing to do is, so what we're going to do for the next sort of 2 weeks, this week and next week, is we're going to talk about searching. And often, the idea is often we're not given an algorithm to solve a problem, but only a specification of what a solution is, and we have to search for a solution. There are lots of cases we're going to look for as we're just told what to do, but not how to do it. And so often this searching is going to be an abstraction of such problems. And a typical sort of problem is where an agent knows its current state. It is a set of deterministic actions it can carry out and wants to get to a goal state. Right? So in a game, we could have you have a particular goal for achieving, and you know your state now, and you have actions you can achieve. If you think about how to plan your career of what courses to take, you could have a goal of having a degree with some specialization, and now each step is taking a course, but you have to have all the prerequisites for it. And so there are some actions you can do of taking courses, and you can get to the goal of having a particular degree. Okay, so this is a common abstraction amongst lots of examples of this idea of a state space search. So you have current state, a set of deterministic actions, and you want to get to a goal state. And from all of these things, we can actually abstract the problem of finding a path in a directed graph. So lots of things we're going to look at later as we're actually going to search for the best solution to some problem. And sometimes it's the best representation for a particular image or something else, but often these we're going to abstract this into the problem of finding a path in a directed graph. And often there's more than one way to represent a problem as a graph, and when we do planning, we're actually going to start off with some representations. We're going to actually examine lots of different ways of representing the same problem as a graph. So a graph here is trying to think about a way to abstract problems, because a lot of what time we're going to abstract problems. All right. So in terms of the state space, in terms of the this dimensions of classification, what we're going to do is we're going to assume it's flat. We're going to have explicit states that we're going to model. We're going to here assume that there's an indefinite stage. So we don't know how many steps we're going to get to achieve the goal, but we'll eventually achieve it. So we don't know how long it's going to take. We're not assuming that we're going on forever. We're assuming the world's fully observable. The actions are deterministic. There are goals. There's a single agent, the knowledge is given, and we have perfect rationality. We can actually solve this problem for doing this. Okay, so in some sense, this is the simplest case that we're going to see in this dimensional space. The only thing that's sort of vaguely interesting is that we're going to look at time going forward. All right. So what we're going to have here is a state space problem. You can have a set of states, a start state. So we're going to have a start with a set of states, a start state, a set of actions, an action function which given a state and returns a new state. We're going to have a way to recognize a goal, and we're going to have this function goal S that's true if S is a goal state. So we're going to have a way to recognize goals and a criterion that specifies the quality of a solution. So you have a set of states, a start state, a goal state, some actions that are going to tell you what to do, and some solution that we want to solve. Okay. So here's an example of a domain that we're going to look at a few times. And here the states the states may be the locations. This is the delivery robot. Right, the locations in bold, right? And the actions can be, you can go to a neighboring location. So the actions are the robot can move to a neighboring location. Boring location. Okay, so you can move to a neighboring location, and we can sort of push doors, right? All right, so they're the actions that we're going to achieve here. And the initial state is you're out in room. The initial state is outside 0103, is in room, is 0103, and the goal state here is, what does it say it is? It's room 123. Okay? And so this is sort of interesting because you can actually get trapped in things. It turns out this, we can only push doors. So once we get into this room, we can only exit through this gate here. So that's why it's sort of interesting. It's sort of misleading as to what's going on. Okay, so that's a sort of abstraction of a problem we're going to look at. Any questions about that? All right. So what we're going to do is we're going to abstract this into into a graph. So we're going to not really assume that we're in terms of states and actions, because later on we're going to abstract things in other ways that aren't necessarily just states. So directed graph consists of a set of nodes and a set of ordered pairs called arcs. I'm assuming people know what a graph is that right? Who doesn't know what a graph is? Who does know what a directed graph is? Oh. Hang on, let's try this again. Who doesn't know about, who hasn't learnt about a directed graph? Who has? Who knows what a directed graph is? Oh, almost the same people who've learnt it. Good. All right. So we're going to talk about a neighbor of a node, saying there is the neighbors of a node, if there's an arc from n1 to n2, so if there's so the arcs are just a set of ordered pairs, so neighbor is just a set of all ordered pairs. A path is a sequence of nodes, so that's at each arc, so it's at each pair of nodes forms an arc. And the length of this path is going to be k, so we're just going to talk about there are k steps in this arc. We're not going to use length very much, we're going to use the cost of arcs. And given a set of start nodes and a goal node, the solution is a path from a start node to the goal node. So the idea is we're going to try to find a path in this graph. So in here, in this one here, this is the same picture we had before. We could actually abstract this as the graph, and we might have 0103 here, and you can go to 0109. Here there are costs on the arcs. And we can go to B3 and B4 and B2. So we want to find a path from here to there. Okay, so we'd like to find a particular path from one location to another in this directed graph. We'd like to find the simplest path in here. All right. The example is Google Maps. So if I look at Google, so if I do Google Maps, then we're trying to find a path from here down to downtown. It's a directed graph because it has to know about one-way streets, but it's trying to find the path that minimizes time. Okay, so it's trying to find a particular path from one location to another that's trying to minimize time, and we'll tell you what it uses later. All right. So here's a robot. Here's another example of a robot cleaner. So here's a simple example. There are 2 rooms and 1 cleaning robot, and the rooms can be clean or dirty, and the robot can either suck or move to the other, make the room clean, or move to the other room, and the goal is to have both rooms clean. So we know what's happening. We have 2 rooms. So how many states are there? How are we representing states? Why are there 2 states? Well, no, there are 2 rooms. Well, but there are how many states of the system are there? So we're going to have, and this was the robot location. So we're going to think of states in here. We're going to think about the state of the world. There are. So what are the states? How many states are there? Yeah. So you want clean robot, dirty. Right, there's either clean, dirty robot, which is so there's a move, right? Whoops, move, and a move. Right, and then you can, what's another state? What happens if you go to clean from this state? So you can suck. What does this give you? Right, so it's clean, clean, and the robots. Right, and then we can move. Right, we can move, goes to clean, clean, the robot is in that room, and we can move again. And I think suck goes there, right? All right, so there's one. So how many states are there? How many states did we say? I can't remember, sorry. What
about both rooms are dirty at the beginning? Both rooms can be dirty at the beginning. I would say like dirty, dirty.
So how many states are there? Presumably this one here is clean, dirty. That's suck, isn't it? Yeah.
I was wondering, so that, for example, we named the room as room A and room B.
Yep.
If both of them are clean and the robot is staying in one room, so the two situations, are they considered as one state or two states?
These two.
Yeah, are they considered two states or one state?
Well, under this representation, the two states, we said. We could do something, another one, yeah.
For the example that you have up there, the dirty, dirty room, can you have like the robot in the right room? Like the right side of the room instead of the left? That'd be another state.
Yeah, it can move. There's no should about it. It's only should if it wants to have the room, if its goal is to have everything clean, it should. But if its goal is to loll about and do nothing, then its goal is to save electricity, then it shouldn't. It should just sit there and do nothing. Depends what its goal is, right?
Oh, the goal is it so would that state ever exist then?
Sure, it could start with that. Presumably one of these is the goal it's going to start with. But it's allowed to move. You're allowed to move. I'm going to define this, and I could have changed the goal around. Yeah, sorry. Yeah, you.
Well, like I was saying, the next state can be like dirty and then clean, right? If you go from top to the
So how many states are there? There are 8 states, right? In this view, there are 8 states. Yeah.
So there's 8 states to like an observer, but shouldn't the robot only be concerned about 2 states because it can't observe the other room while it's being clean, right?
Oh, but then it still is dirty or clean.
But the robot itself is operating like, is the room I'm currently in dirty or clean? It's
So-
only concerned about that. And then when it moves, it switches back to like, is the room I'm in dirty or clean? It doesn't know about like the other room because that's uncertain, right? Someone could
Yep, the problem if you have a forgetful agent that doesn't remember whether the other room is thing, it's actually never going to stop and say, I finished. It doesn't know if it's finished. right? Because it goes to this room's dirty, and it wonders, oh, should the other room be, I don't know about the other room now, I've forgotten whether I cleaned it or not, right? It's sort of getting forgetful. So you need to model this, you need to model those as different states. So here we're assuming it's fully observable. But you're on the right track. You can do better than 8 states. How can we do better than this? Yeah.
You can add a state where like the room after like 1 day or something is stale and you check it or something.
No, this time problem, we can solve it with fewer than 8 states. How can we do this? Yeah. Well, here we're sort of 3 features. There's sort of 3 features here almost. There's the feature whether the C is in the left and the right. The features whether the right room is dirty, and the other one's where the robot's in the left room or the right room. So here there are sort of 3 features, and that's how I got to 8, by knowing that there are 3 features. But you're actually not reducing the state space, because all of them are possible, right? Because you can move around between all of them, yeah.
We've given sort of absolute location to the rooms and located the robot in them, but if you just said current room and other room,
Yeah.
collapse each of those steps.
That's right. So you can get to the 4 states by having the robot room, a pair of the robot room and the other room, or whether that's clean or not. So you could have clean, dirty, and you can move and you get to dirty, clean. Right, and from here you can go to, here you can suck and get to clean, 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 and you can start with dirty, dirty, and you can clean. And these have interesting things. As you move, you get the same thing. Okay, so here we can have this, we can represent this in terms of just four states by talking about about how we're abstracting this problem is the way that we're going to do this. A lot of what we're doing is actually trying to find good representations about how to represent things so that the problems become simple. Because sometimes problems are simple if you represent them a certain way, and sometimes they're complicated. So we would like to find representations that are actually as simple as you can get them. Okay. Okay, so we have this thing. So representations are going to be important. So a lot of what we're going to do is to think about how to go about representing problems in certain ways. All right. So there's another one. Here's you have a game. This robot that's called Rob. We keep calling our robots Rob. Needs to collect coins C1, C2, C3, and C4 without running out of fuel and end up at location 1, 1. And it can visit this fuel location. It gives it 20 units of fuel. And it starts at 5, 8 with 6 units of fuel. And it can go up, down, left, right, as long as it doesn't crash into the wall. Right here's sort of an abstraction of a sort of the game that you might have. Okay, so there are things to collect. So what's a state in here? So what might be a state? So what might be a state in this video game, this computer game we could play? So what information is important to know what? So you have to have the information has to be enough so that you know whether you're at a goal, and you have to know the effect of actions. Right, so what could be the state? Yeah. So you just want a location. That's right, X, Y, and the amount of fuel.
I guess what coins you have. Because your goal is you're trying to collect coins.
Right, so how might you represent what coins you have? Yeah, so you can think about having coin 1, coin 2, coin 3, and coin 4. Right. There might be a state of the world. So your XY position of this is the XY position of Rob, the amount of fuel they have, and whether they have these 4 coins. And notice here there are 8 combinations here, but there are 8 subsets of sets of coins. You're not going to do much better in the terms of the representation of states than this, right? Because you can just do counting arguments. If there were fewer, right? So the fact that there are 8 different combinations means that 4 bits are actually reasonably good representation for this. And then the amount of fuel, which is the amount of fuel you have, so in here. Okay, does that make sense? So here's an example of doing that. So here we had, I paid him a lot to say this. You have the state, so the X position, the Y position, the fuel, and this coin. So you can start off with the position 5, 8. You have 6 units of fuel. You can go, this says that you don't have coin 1, you do have coin 2, you don't have coin 3. So you could go up to position 5, 9 and reduce the amount of fuel you have. And then you could go left to 4, 9, right? And then you increase your number of, you get 20 units of fuel, right? So you can think about in here, this just terms of state space here, as we're just moving from 5, 8, we're reducing the number of coins, this. And we only change the number of coins when we visit the state. So if we go to 5, 7, then coin 3 becomes true. Okay, yeah.
So is this game like fully observable or partial in this case?
So in this case, we're assuming that fully observable. So this case here, we're assuming it's a fully observable game. We know what's actually going on here. Yeah, so the current abstraction, things are fully observable. Things get partially observable later, but for the moment we're assuming. Well, yeah, in fact, it sort of doesn't matter for this representing things in terms of state spaces. Even when we have partially observable systems, we often have a state space, even though we don't necessarily know everything. And here the goal is we don't care. We have to have, 1, 1, or all those things to be true in a location 1, 1. And for anything which has any amount of fuel in there, we don't have to have any particular amount of fuel in there. Well, that's our goal state. Okay? Questions about that? So we're going to abstract, yes?
What's the advantage of doing all the coins as like true, false, Boolean values as opposed to just doing like a count of 4 and like the goal is to have 4 coins?
Because if I'm at this, that doesn't provide enough information to know what the next state is. So if I know that I'm at position 5, 8, right, and I have with 2 coins, right, and I move down, what's the resulting state? I'm at location 5, 7, but I don't know whether I have 3 coins or 2 coins, because I don't know whether these two coins include C3. So I should collect C3, right? So should collect C3, but only if I don't have it. Right, so when I go down, I have to collect C3. But knowing that I only have 2 coins here doesn't provide enough information to be able to predict the next state. In this one here, my actions are not observable.
So that means that once you collect the coin, Rob still knows where that coin was?
Well, it has to know. It has.
So you're saying that once you collect the coin doesn't actually go away. You still know where the coin is.
Rob has to. Well, this isn't telling you very much about that. This abstraction is not telling you that, but it's telling you that Rob has to know. You have to model about whether Rob has coin 3 or not. When we go there, so if the 2 coins included coin C3, then we go to here. We still only has 2 coins. But if the coin didn't include C3, then he go down here. He has to now has 3 coins. So just knowing the number of coins doesn't provide enough information to know what the effect of actions is. Right, so that's important here, is that we need to model about, because action, so the states have to convey enough information to both tell whether something is a goal and to be able to predict the effect of actions. So the states, let's write that down, the states need to provide enough information to both to predict the effect of actions and to know if a goal has been, and to know if a goal has been reached. Okay, so in this case here, this is not enough information. It's enough information to know whether a goal's reached, but it's not information to know the effect of actions. I could imagine here, if I didn't model the coins he had, I know the effect of actions. So if I wasn't modeling the coins at all, but I just couldn't tell if you're at a goal state. So if I didn't model which coins they had, if I didn't model anything about coins, I know how to predict the next state, but I don't know how to check whether you're at a goal state. The fuel here is useful because it only lets you move down if you're going to have enough fuel, so you can't move. So the fuel is important for that. Okay, questions about that? Yeah.
Sorry, this might be a trivial question, but for the goal, shouldn't it, instead of the question mark, shouldn't it be like greater than 0? Because of the state, it says like the goal of the game is to get to like the point without running out of fuel.
Yeah.
And then you also want to collect 4 coins.
Yeah, I'm assuming that you actually can't get to a state which is below 0.
No, I mean like if you get to the bridge 1, 1, 1, 1 with 0 fuel, then you either win the game or lose the game. Because I know that some games, like if you get to like the end goal with the 4 coins or something, and then if you get there with 0 fuel, you either win the game or you lose the game, depending on how the game is set up, right? So
Yes, that way here you could model how the goal. Yeah, so that's just part of defining this goal. So here I just assumed here that you just couldn't move if you had no fuel.
no, like if it goes from like let's say 1, 2 to 1, 1 with only 1 block of fuel, then by the time it reaches 1, 1, it would be at 0 fuel, and then.
That's fine.
Yeah, I don't know. Like for this, I guess for this game it's fine, but for other games, like if you get to that goal endpoint goal with 0 fuel, you like sometimes lose the game.
Yeah, so it depends on the rules of the thing. So all of these things, but we know enough information. But the point of this is we sort of have enough information to know what it is we need to define, right? We need to define these things. We need to define what's a start state, what's a goal, how can we move. They're the rules of the game. They're all we need to specify. That's the abstraction we're doing. All right. All right. So here's the algorithm I'm going to do. So what I'm going to do is, there's this generic search algorithm. It's given a graph, a start state, and goal node. It's going to incrementally explore paths from the start node. So it's going to incrementally explore paths. And you're going to maintain a frontier of paths from the start node that have been explored. So we're going to maintain this frontier. So we're going to start with a start node